Good morning, everybody. In this new term, the optional paper for mathematics is there, which is named as Higher Mathematics. For electronics group, the course code is EIF 312 312 EIF 312, and for mechanical, the code for higher mathematics is MEF 313 313. So this is very important topic to study. First I will give the outline of the syllabus. For electronics and for mechanical also, section 1 is common, and there are two topics only in section 1. First one is finite differences, and second one is partial differentiation. And in section 2 also one topic is common for mechanical as well as electronics group. So the common topic is Laplace transform in section 2, and for mechanical the remaining topic in section 2 is linear differential equations with constant coefficients, LD, the short form of which is LDE. And for electronics, the second topic for section 2 is Fourier series. So this one is the outline of the syllabus. We start from the topic from section 2, that is Laplace transform. So the first topic to study is from section 2, and it is named as Laplace transform. So the brief introduction is given. The governing principle behind any transformation is as follows. Using a transform, a problem in the given domain can be converted into another domain with the hope that its solution in the new domain can easily be found out. Once we obtain the solution in the new domain, we come back to the original domain and have the solution to the given problem. This to and fro process is termed as taking the transform and taking inverse transform. The solution of most electrical circuit problems can be reduced ultimately to the solution of differential equations. Thus, Laplace transform is useful in solving differential equations. So why we study this Laplace transform? Because its major application is to solve differential equations, and differential equations are very useful. It has many applications, and therefore Laplace transform is also equally important. The After introduction, the next point is we define Laplace transformation. So definition of Laplace transform. This is 2-mark question and can be asked many times. The Laplace transform of ft, function ft, is denoted by L of ft or f bar s, and is defined as L of ft equal to f bar s is equal to integral 0 to infinity e raised to minus st into ft dt, where s is a parameter. So Laplace transform definition is like this. Laplace of ft is also denoted by f bar s because it is in terms of s, therefore f bar s, and it is equal to integral 0 to infinity e raised to minus st into ft dt, where s is a parameter assumed to be a positive real number. S is a parameter assumed to be a positive real numbers. So with this definition, or using this definition, we will see some Laplace transform of some elementary functions. So these are the standard formulae we will say. So Laplace of first formula is Laplace of e raised to at is equal to 1 upon s minus a. So we try to prove this also. Ft is e raised to at. So Laplace of at by definition integral 0 to infinity e raised to minus st into ft. Ft is e raised to at dt. So this is integral 0 to infinity e raised to a minus s bracket into bracket a minus s t dt, and its integration is e raised to a minus s into t divided by a minus s. The limits are 0 and infinity. So using the upper limit, this e raised to at e raised to minus st, this becomes 0, and lower limit is a, so e raised to this is e raised to 0. E raised to 0 is 1. So 1 upon a minus s minus of 1 upon a minus s, or 1 upon s minus a. This minus sign we operate here, so that the final answer we were getting is 1 upon s minus a. So see once again, Laplace of e raised to at is equal to 1 upon s minus a. How? This is also very important formula. You have to memorize this in solving the examples. So you treat this as a formula, standard formula, like in the integration or in the derivative also you have seen various formulas. So likewise you treat this as a standard formula and memorize it when needed. So Laplace of e raised to at is 1 upon s minus a. So its proof is like this: integral 0 to infinity e raised to minus st e raised to at dt e raised to integral 0 to infinity e raised to into bracket a minus s into t dt. So e raised to a minus s minus a into t dt divided by a minus s. This is the answer for the integration, and with the first limit, upper limit, the value is 0, and lower limit 1 upon a minus s. So this minus sign we operate here, and we can get the answer as 1 upon s minus a. So second formula is Laplace of 1 is equal to 1 upon s. So here only you put t is equal to 0, t is equal to 0, a is equal to 0, not t is equal to 0. Putting a is equal to 0, we will get Laplace of 1 is equal to 1 upon s minus 0, that is 1 upon s. So second formula is Laplace of 1 is equal to 1 upon s. Actually this is the corollary of this one. Putting a equal to 0 in this formula, we will get Laplace of 1 is equal to 1 upon s. So we are using these formulae in solving the examples. We will see when we solve examples on Laplace transform how we can use this. Third formula is Laplace of sine at is a upon s square minus a upon s square plus a square. So ft sine at, again by definition, Laplace of sine at is integral 0 to infinity. E raised to minus st is always fixed, and only ft we have to change, sine at dt. So using this formula, we can get, this is the standard formula from integration, and we can get it like this, 1 upon a square plus a square and into bracket and so on. So that we will get the final answer as Laplace of sine at equal to a upon s square plus a square. The third formula is Laplace of cos at s upon a square plus a square. Ft is cos at, Laplace of ft is Laplace of cos at. Again ft is changed here, cos at is here. Again from the integration topic which you have seen in the last semester, this one is again the standard formula, and using the limits we can get the value of this integration as s upon s square plus a square. Then see, first formula is Laplace of e raised to at, that is 1 upon s minus a. Second formula is Laplace of 1 upon s. Third formula is Laplace of sine at, a upon s square plus a square. Fourth formula is Laplace of cos at, s upon s square plus a square. And now we will see the fifth one, Laplace of sine hyperbolic at is a upon a square minus a square. So sine hyperbolic at, the definition of sine hyperbolic is like this. For mechanical students, this definition is new, so keep this in mind. Try to write all these things on paper. Sine hyperbolic at is e raised to at minus e raised to minus at divided by 2. This is the definition of hyperbolic function. This is not sine h at. This is sine hyperbolic at, pronounced like this. Then we have to see how it comes. Laplace of ft equal to Laplace of sine hyperbolic at. So Laplace of sine hyperbolic at, the definition is e raised to at minus e raised to minus at divided by 2. That is half Laplace of e raised to at minus half Laplace of e raised to minus at. Laplace of e raised to at we have already seen, 1 upon s minus a. This is 1 upon s plus a. Then try to simplify this, and finally you are getting the answer for Laplace of sine hyperbolic at equal to a upon s square minus a square. Laplace of sine hyperbolic at is a upon s square minus a square. The next is Laplace of cos hyperbolic at, that is s upon s square minus a square. Again use the definition of hyperbolic function. Cos hyperbolic at is e raised to at plus e raised to minus at divided by 2. For mechanical, again I am telling you, for mechanical this concept is new, and use the definitions of hyperbolic function. This is not cos h at, this is cos hyperbolic at. So cos hyperbolic at is like this, e raised to at plus e raised to minus at divided by 2. And therefore Laplace of cos hyperbolic at is Laplace of e raised to at plus e raised to minus at divided by 2. Again try to take the separate Laplace. Laplace of e raised to at, half is there, and half is there, again Laplace of e raised to minus at. And try to simplify this. You are getting this as s upon s square minus a square. S upon s square minus a square. So finally we are getting Laplace of cos hyperbolic at equal to s upon s square minus a square. The next formula is Laplace of t raised to n, that is n factorial s raised to n plus 1. I suppose all of you know the factorial notation. N factorial is product of first n natural numbers. Product of first n natural numbers, n factorial. So ft is t raised to n, Laplace of t raised to n is integral 0 to infinity e raised to minus st into t raised to n dt. Put st equal to u, so that t equal to u by s. Differentiate with respect to u. S dt equal to du. Dt is du by s. Limit will change. The changed limits are also the same. For u, the limits are changed. E raised to minus u by s raised to n du by s, that is 1 upon s raised to n plus 1 integral 0 to infinity e raised to minus u raised to n du. Here we use the definition of gamma function. Gamma function, actually in the syllabus, whatever we have covered up to the last semester, this topic was not there. So gamma function, use the definition of gamma function. Gamma n, this is the notation, gamma n. Gamma n is integral 0 to infinity e raised to minus x raised to n minus 1 dx. So Laplace of t raised to n is 1 upon s raised to n plus 1 gamma of n plus 1. But gamma of n plus 1 is equal to n factorial. Again, you just take it as it is, because this is the result from gamma function. Gamma of n plus 1 is equal to n factorial. And therefore, finally, we are getting Laplace of t raised to n is equal to n factorial divided by s raised to n plus 1. So that we can find Laplace of t square. N is 2 factorial upon s raised to 3. Laplace of t cube, 3 factorial upon s raised to 4. Like this. 3 factorial is 6. So in solving the examples, we have to use all these results. Then some properties of Laplace transform. Linearity property, Laplace of a into f. Actually we have used in the proofs also, but it must be noted here. You just write it down. Laplace of a f1t plus b f2t equal to a into Laplace of f1t plus b into Laplace of f2t. So this is the linearity property commonly used in various proofs or in solving various examples. So this is about the Laplace transform formulae. In the next lecture, we will see some examples on Laplace transform. So for today, it is sufficient. I will just revise what is meant by Laplace transform. Laplace transform of the function ft is Laplace of ft equal to integral 0 to infinity e raised to minus st ft dt. This is the definition of Laplace transform. And the answer for the integration comes out to be in terms of s. Therefore, it is denoted by f bar s. So f bar s or Laplace of ft equal to integral 0 to infinity e raised to minus st ft dt. And using this definition, we have seen or we have proved some results. The first one is Laplace of e raised to at, that is 1 upon s minus a. Its corollary, that is putting a equal to 0 in that result, we will get the next result as Laplace of 1 equal to 1 by s. Then Laplace of sine at equal to a upon s square plus a square. Laplace of cos at s upon s square plus a square. Then Laplace of sine hyperbolic at a upon s square minus a square. Laplace of cos hyperbolic at s upon s square minus a square. and Laplace of t raised to n equal to n factorial divided by s raised to n plus 1. So actually this topic is written by me, and this is my book, and therefore I am not giving the separate notes of this. These are the notes. So you go through all these things, and if you are having any difficulty in understanding the concept or in the proofs, so you please ask me. So for today it is sufficient. Stay home, stay safe. Thank you very much.